All right, so numbers can come in all these different forms. I want to make very clear, when I say number, I don't just mean constants. I mean variables. I mean entire expressions. I mean function outputs, all right? Okay, so now that we've got this notion of like the numbers that we're working with, let's talk about the operations. These are the fundamental operations of algebra. We have addition, multiplication, and powers, or exponentiation. So notably absent from this list is like subtraction and division, which are often listed as fundamental operations, but they're not fundamental, as we'll see, right? You may recall that subtraction and division are really just sort of special cases of addition and multiplication. We'll get to that in a moment. So these are our fundamental operations: addition, multiplication, and powers. We have some properties. There's lots of different algebraic properties that we use when we're performing algebra, but I would want to go over like the most basic ones here. We'll do others when they become relevant later. So the first one, the first two, I'm sure you've probably heard of all of these, but the first two are very familiar, almost second nature. Commutative and associative properties. Commutative means that when you're combining things with addition, the order of the numbers that you are combining doesn't matter. A plus B is the same as B plus A. We can swap that order, and it doesn't affect the outcome. Same is true for multiplication. And by the way, I'm using this dot for multiplication, but I could be just using, juxtaposition, putting them next to each other, like I did here. So sometimes I'm going to write the dot if I want to make very clear, like if I want to draw attention to what operation I'm talking about, but other times I'll just write the numbers next to each other, and yeah, you know what I mean. Okay, so commutative is that. Associative has to do with when you're doing more than one operation, what order are you going to evaluate the operations in? And so if you take three numbers and you're adding them all together, a plus b plus c, we could, in one case, do a plus b first and evaluate that addition, and then take the result of that and then evaluate adding with c, right? And so we're evaluating this second addition second. Alternatively, we can rearrange where the parentheses are and say, let's do the b plus c first, and then take that result and do a plus that. So we're evaluating the second addition first and the first addition second. So the order in which you evaluate those operations here doesn't matter. That's the associative property. And the same is true here with multiplication. All right. So the next property here is the distributive property. And I actually wrote distributive properties because there are two that I want to share with you. So the first one deals with when you are combining multiplication and addition. So I'm going to write a plus b and then that whole sum times c. Now, when we have a combination like this, we say that the multiplication distributes over the addition. So we actually end up with a times c plus b times c. This, I hope, is very familiar. Okay. That's a distributive property. But there's a second distributive property which uses different operations. It works like this. If you have a times b, and you're taking that product to the power of some other number, c, then this is the same as a to the power c times b to the power c. This rule is not always presented as a distributive property, because I think some people think it's confusing, but I think it's very useful to think of it as a type of distributive property, because if you compare it to this familiar distributive property, they're like the same thing, except all the operations are sort of shifted up one level, right? If you think of the operations as being in a hierarchy, you got addition, and then multiplication is like repeated addition, and powers are like repeated multiplication. We see the multiplication distributes over addition, and then shift that up, and the powers distribute over multiplication. Right? So two different distributive laws. But it's very important to notice that these are the only two. In particular, the powers do not distribute over addition. This is one of the most common mistakes that you see in algebra, and I'm sure everybody is familiar with this mistake because you've either made it or your professors, past professors or teachers have talked about it. It's just like a running joke almost. But I'm just pointing this out. So the types of distribution which are allowed are these two types, and the powers simply do not distribute over addition. You try it out, and it just doesn't work. So yeah, so try to avoid that. All right, the last two properties here that I want to go over, identity and inverse. These two are in some ways more important than the first three, because we're going to use the identity and the inverse properties all the time without even knowing it in many cases. So first, the identity properties have to do with what do you add or what do you multiply by if you want to do nothing. Say I've added A and I want to add something else to undo the adding of A. Or sorry, no, I got ahead of myself. That's inverse. Say I want to have A and I want to add something which is going to do nothing to it. Well, if I add 0, that doesn't do anything, right? Because I just still have A. So that means that 0 is the additive identity element. It is the unique and only number that you can add if you want to do nothing, right? Same with multiplying. There is a number, a single unique number, which if you multiply by it, it does nothing, and that number is 1. So 1 is our multiplicative identity element. They're unique, right? So these two numbers are super special. And then the inverse properties deal with those numbers as well. Inverse properties are like this. If you have added A and you want to add something to undo the A and get back to nothing, so get back to 0, what are you going to add? Well, you're going to add negative A. It's called the opposite, right? A and negative A would be opposites. This could be like 5 and negative 5. It could be like negative pi and positive pi, whatever. They're opposites. If you add them, you get 0. So this gives us a way of undoing addition by adding the opposite and getting back to adding 0, which does nothing, and so we can omit it. All right, this is something we do all the time. You'll see in an example in a later video. With multiplication, again, if we have multiplied by A, but we want to undo that, what would we multiply by to get back to nothing? Well, in the multiplicative sense, nothing is 1. So to get back to 1, we would multiply by 1 over A. So this is essentially like dividing by A and giving us 1. A over A is 1. So this is where subtraction and division come from. They're really just, subtraction and division are just the inverse properties of addition and multiplication, right? So there we go. So that will do for now. I'm going to flip this paper over and just wrap this video up with a couple of vocabulary points. All right, I'm a big stickler for vocabulary because I think it's really valuable. It's useful to use correct vocabulary. So we're going to make a few important distinctions. The first one is sum versus product. These words mean different things. A sum is what you get when you add some things together. So like A plus B plus C is an example of a sum. A product is when you multiply some things together. Right? Okay. When you have a sum, the numbers that are being added together to create that sum, those are called the terms. So terms. And then if you have a product, the numbers that are being multiplied together are called the factors. So this vocab distinction is really important. Terms versus factors. When you're doing algebra and learning how to, perform algebraic manipulations to simplify things or just solve for things or whatever, distinguishing between terms and factors is really important, especially when you're like simplifying fractions or something, right? You've got to understand what a factor is, and you've got to understand when you're looking at a product versus when you're looking at a sum, okay? So just for example, if you have like 2 times x plus 7, this algebraic expression overall is a product with 2 factors. It's got 2, and it's got this x plus 7. Those are the 2 factors. Now, one of those factors, the x plus 7, happens to have 2 terms within it, okay? But the terms x and 7 are not terms of this whole algebraic expression. They're just terms of one of its factors. right? So overall, it is a product with two factors. You can't say that this expression has 7 as a term, right? Because it doesn't. If you want to think about this thing as being a sum, then you'd have to apply your distributive law and get 2x plus 14, right? Now it's a sum. Now it's not a product any longer. Overall, this expression is a sum, and it has two terms. One of those terms, 2x, happens to be a product with two factors. Get where I'm going with this? So understanding this this distinction is really, really valuable, especially if you want to do something like cancel common factors. If you're going to cancel common factors, you got to have factors, which means you've got to have a product, which means you might have to do some factoring from this form into this form in order to get the product with the factor you need that you might want to cancel or whatever. So get where I'm going with this. This vocabulary is really important. Having words, having different words for these things gives us, just helps your brain distinguish between these cases. If we didn't have different vocabulary for these two things, if we called them all the same, then I think it would just get confusing and it would be harder for us to like conceptualize the distinction. So yeah, I'm going to try to be super careful with using that vocabulary, and I would like you to do the same. One more vocab distinction that I think is really important is expressions versus equations. All right, two mathy words that both begin with E, but they are different, right? An expression is usually short for algebraic expression or mathematical expression, right? That's a number. We just talked about that. That's just a number, right? It's like some other numbers combined together with operations or perhaps functions. But notably, it's just a number. An equation, on the other hand, has an equal sign in it. It's right in the name, right? It comes from the word equals. So if you have two expressions which are equal to one another, then we have an equation, and an equation can be solved. You can't solve an expression. You can evaluate an expression if you specify the value of any variables that are in it, but you can't solve it. That doesn't make any sense. Solving an equation, though, is something you can do. You can search for values of those variables that are going to solve it, right? You can have expressions that are equivalent to each other because they would always have the same value when you evaluate them. And you can have equations which are equivalent to each other in the sense that they have the same exact solutions. And you can kind of get from one to the other by some algebraic manipulation. But the expressions and equations are still very different things that we use differently. So yeah. Okay, I think that's the end of the first video.